Recording in progress. Okay. Question number 64. Which species has the largest radius? So what's unique about all of these species right here?
I mean, most of them have or islands, except for the
Indeed. So what's special about these? Like in the periodic table, where are they located?
main group.
Or are they like, okay, let me phrase it this way. Are all these elements like close to each other or far apart on the periodic table?
Close. Because some of them are like in groups 1 and 2, and the others are like group 17 and 18. Oh,
I'm saying atomic number is. What's the atomic number of xenon? Yeah, Taylor basically said the word I was trying to beat out of y'all. It's called isoelectronic series. These are isoelectronic series. So what that basically means, since some of y'all haven't learned it yet, is basically all these ions right here will have the same configuration as xenon, as a certain normal gas. Like if you look at it this way, tellurium, if we look at our periodic table, tellurium is 2 away from xenon. So Te2 minus would add 2 electrons, right? So the electron configuration of Te2 minus would be identical to what?
okay, so basically isoelectronic means it's like multiple electrons with the same configuration.
Yeah, multiple elements with same configuration. Multiple elements with the same configuration. So as I've stated before, all of these elements have the electron configuration xenon. So if we keep going right here, so we have xenon, or let's write these out. So it's, if you look at the periodic table, it's antimony, tellurium, iodine, xenon. Then over here it's cesium and then barium. So as I said before, all of these have the same electron configuration as xenon. So now we know this fact, right? So now let's look at the cation. So that's Ba2 plus and cesium plus. What's true about cations atomic radius in reference to the parent atom? Cations are smaller. Cations are smaller. So cations are smaller than parents. And what about anions? Yeah, anions are larger than. So cations are smaller, anions are larger. That's basically the whole point of trying. But of these, if anions are larger than the parent atom and cations are smaller, would a species that's an anion have a larger radius or a cation? Yeah. So what we're looking for is basically in any isoelectronic series question, isoelectronic series, we're looking for the anion with greatest negative charge. As that one will have your largest radius because it's larger than your parent atom, and yeah, it's basically the most negative out of it. So it's the most anionic in character. So if it's more anionic in character, it's larger in radius. So which of these is the most negative? Yeah, antimony 3 minus. So we're gonna go with option E. And that is our answer for number 60.
What would be the answer if the question was asking about the shortest radius?
I would say so. So Ba2 plus would have shortest.
And I'm assuming the reasoning behind why it's like a larger radius is because it's more negative, is because there's more electrons like I guess, crammed into the shell.
Yeah, more electrons, and we know electrons, they have electron repulsion, so they want to spread out further.
Thank you.
Yeah, so sum it up, isoelectronic species, they're species that are like. There are different elements, but they have the same electron configuration. So yeah, multiple elements, same configuration. Cations are smaller than the parent atom, anions are larger than the parent atom. And we're looking for the anion with the greatest negative charge, which will have our greatest radius. Questions on that?
You can go eat your sandwich.
All right. Man, like Dylan, gonna take over the next question.
All right. So. Let's see. Do y'all want me to make another isoelectronic question on the spot or what? Okay. What is this?
No.
Interesting. Okay. Let's go to the new one. So let's do the unlike Rich. I don't have the periodic table memorized since I was the age of 4. So I'm gonna have to look at this thing and make one up ourselves. So that one's easy, but we'll go with something I know. All right. Okay. So if we had these elements and we were asked, which of these, they're not elements at this point, they're ions except for argon. Which of these species is going to have the smallest and which one's going to have the largest radius? First, let's answer the smallest question. So which one has smallest radius? So disregard question 65, just for right now. We're not focusing on the question 65. All right, so this guy's all right. Yeah, so Sydney says that scandium 3+ is going to have the smallest, and I have to agree with Sydney. And let's just take a look at the principles that allow or that make scandium have the smallest. And if we look at the atomic number of any atom or element on the periodic table tells us how many what? Electrons, but more specifically, the atomic number tells us the number of protons in the nucleus, right? So scandium has 21. That means potassium would have 19. And then we have 20 or 18 here. And 17, 16, and 15. So, but we know that we realize that they all have the same amount of electrons, right? So let's just draw a general nucleus. And they all have, let's just say 8 valence electrons, right? So 1, 2, 3, 4, 5, 6, and then we have 7 and 8. So we know that, do we all agree that they all have the same amount of valence electrons because they are all isoelectronic species? Do we agree on that? Yes or no? Because if not, then you won't understand the next part. Right? Okay. Perfect. So if we can agree on that, then we realize that the one that has the greatest charge in the nucleus is going to have the smallest radius. So if we look at this column on the left, the one that has, scandium has the greatest charge in the nucleus. It has 21 protons. That means it has a charge of plus 21. Let's just simplify it and say coulombs, right? Or let's just leave out units for simplicity. But let's just say it has a charge of plus 21. And do we all know about Coulombic attraction and stuff? So basically, there's this equation that says the force, the electric force is proportional to the charges. And we know that the bigger the force, the stronger, or the bigger the charge, the stronger the force. So if we all have the same number of electrons in the outermost shell, the bigger the charge is in the nucleus, it's going to want to pull on these electrons further in, which is why we see scandium. They all have the same amount of valence electrons, but scandium has the biggest charge, so it's going to have a radius of, let's just say, for simplicity, 10 meters. Okay, that's not going to be true, but 10 meters. Obviously, atoms are not this big. And say we had phosphorus on the other hand, phosphorus would be 15, a charge of 15 in the nucleus, so 15 plus. And then we know that because it doesn't have as big of a charge as scandium, it's not going to pull on those outer electrons as well as scandium. So its radius is going to be a lot bigger. 5, 6, 7, 8. So because the charge in the nucleus for phosphorus is not as strong as the charge in the nucleus for scandium, and there's the same amount of valence electrons, scandium will pull these in further, causing it to have the smallest radius, whereas phosphorus is not going to be able to pull it in as far, causing it to have a larger radius. Let's just say this was twice, so 20 meters in radius. So if you were, that's basically the physical aspect behind why this is the case. But if you're given an isoelectronic series, you're either going to be asked to identify the smallest ion or smallest species or the largest. You can't really go in between, right? So you're either looking at the one side of the spectrum with the most negative charge, the 3-, or the most positive charge, 3+. Phosphorus with the 3- charge would be the biggest or the smallest. What do we say? Biggest, right? Whereas scandium is going to be the smallest. And it all has to do with the amount of charge in the nucleus. So, what did y'all already learn that? I think y'all did, right?
Not the equation for that, but
Yeah, I think that's just an equation from physics that you will have to learn that for the final, because there's like one question on the final about something called lattice energy, which
what was it?
it's called, this is the equation, and it's called the Coulomb force or Coulombic force, Q1 Q2 over R squared. And we actually have a YouTube video called Lattice Energy, and you should watch it now and maybe a couple more times before the final exam, because it's something that's very important, and there's for sure a question on it on your final. Yes, that's it. All right, so let's go ahead and jump straight to 65, where we're talking about what's the principle that we're dealing with here. We're talking about lone pairs and sulfur hexafluoride. We're probably talking about Lewis structures, right? So how would you know how many lone pairs of electrons does sulfur hexafluoride have? And let's be specific. Let's say on the sulfur atom. So we're talking about on the sulfur atom, which, if it's not obvious, sulfur would be the central atom. So what's the first step of doing this?
Right.
You just know, yeah. So let's go ahead and draw it out. for good practice. So what's the first step before you draw anything out? You count up how many valence electrons you have. How many valence electrons does sulfur bring to the table? 6, and each fluorine brings how many? 7. We have 6 fluorines because the name tells us hexafluorine. So 6 and 6 times 7 is 42, plus 6 is 48. Okay, so from there we would just do 6 bonds. That's 4. So we would have something like this, all of our terminal atoms. And then we would subtract how many electrons we've used so far. So how many have we used so far? Well, we've used 12. We have 6 bonds, right? So we would do minus 12. This will give us 36. And we know each fluorine needs how many more electrons to be happy. Right? Because each fluorine right now is sharing 2 electrons. So it has 2 electrons right now. And it needs 2, 4, 6 more to complete its octet. So we need 6 on each fluorine. We would put 1, 2, 3, 4, 5, 6. And let's just, I guess I'll do it so I don't confuse it. I just was going to start doing lines. Okay. So we used up 6, 12, 18, 24, 30, 36. Minus 36 will give us 0. So no lone pairs are put onto the sulfur. And the fastest way to actually figure out this problem is knowing that the maximum number of bonds the central atom will have for this class specifically is 6. So you can't go over 6, meaning the maximum number of electrons that the central atom can have is 12 valence electrons. So you can never have over 6 in this class. So if it's sulfur hexafluoride, you know there's 6 fluorines around it. You know the sulfur can't have any more lone pairs on it because it's already maxed out. Therefore, answer would be A without having to do all that work. But you could do the work and see for yourself that there is no lone pairs on that.
Or you can do that math trick I taught y'all.
That is also true. So the math trick Rich said is you take the number of you take the number of terminal atoms. So we have 6 fluorines as our terminal atom, and you multiply that by 8. You get 48. You do 48 minus 48, which is obviously 0.
So more than likely, we're gonna get asked a question about the central atom.
Oh yeah, most definitely. You're never going to be asked how many lone pairs is on the terminal atom. It's more likely central atom. Yeah, what's up? Okay, so because we have 6 terminal atoms and each one needs 8 electrons. So we do 6 terminal atoms times the 8 that are required, which gives you 48 electrons that are required to be put either in a bond or on lone pairs on the terminal atoms. So then when you have we only have 48 electrons to deal with. So we do 48 minus the required 48 for the terminal atom. So you end up with 0 excess, meaning you have 0 lone pairs on the central atom. Anyways, good questions. If there's none, let's go ahead and do a throwback Thursday question. I came up with that on the spot. So this is something we talked about a while back. Let me go ahead and tell me which one y'all are thinking. Which of the following transitions has the least energetic photon absorbed? If we're absorbing a photon, we are going from a what state to a what? Like a low or to high or high to a low energy state? Low to high. So we should be looking for an answer that is going from a smaller number to a bigger number. So we can cross out A, we can cross out B, we can cross out E. So we're left between C and D. And which one do you think it is? Okay, we got one person that says C. We got one person that says D.
Raise your hand if you think C. I would price. No,
All of a sudden, Robbie, really?
we need to take a vote.
All right, John says C. John with his spicy spaghetti over there. Well, because you haven't been coming, so I don't know what to say to you. Okay, we got one person that's
Two
two people
people,
that they see.
3 people that they see.
The answer to question 66 about which of the following transitions has the least energetic photon absorbed is answer choice D. All right, so the way to think about this is, let's say we have our nucleus, energy level 1. Let's say it has an electron there. So this is energy level 1. This is energy level 2. This is energy level 3. And then let's go all the way to 4 first. So, well, and each energy level has their electron on it. So to eject a photon all the way in energy level 1, you have to have a pretty high energy photon to go through all these other energy levels to go all the way to the first energy level and then eject an electron. Or, yeah, well, not ejecting electron, but it's reaching the electron down there, which means that photon must have a very high energy for it to go from past all these other electrons and want to go towards the most difficult electrons to reach. Whereas the 4th energy level is further out from the nucleus, so you don't need as much of an energetic photon to reach the electrons on the 4th energy level, which is why answer choice is D. Is there any questions? I know some people were saying, if you said C, does it make sense why it's not C now?
Yeah.
Okay, good. And if you said D, did you just guess? This guy Daniel got his money. And I know you for sure did not guess, right? You knew that.
I thought it was like the greatest difference between like.
Yeah,
the difference between, like, you-
not necessarily. You can also kind of think about it like this. Yeah, so you can also kind of think about it like this. If the electron were to return from its excited state to its ground state, let's say 7 to 4. So n equals 7 to n equals 4. And versus n equals where is it? N equals 3 to n equals 1. Because energy is conserved, it's going to emit a photon in the same region of the electromagnetic spectrum that it absorbed a photon. So which one's going to emit a photon of the higher energy the higher wave, the shorter wavelength, or you can say higher energy. That would be the bottom one, right? Because it's a Lyman series, and we know that ejects a photon in the UV region, which is going to, for this class, you don't learn anything else that can eject photons in the gamma and cosmic ray region, just because usually the stuff doing that is going to be like stars. But for hydrogen atoms, the most it gets is UV region. So that's why it would be answer choice D, because this would release a photon in the UV region, this would probably release something even I guess way lower in energy than infrared. But Sydney asked a question saying, is this going to be on the exam? And I would say that this is a totally fair game to put on the exam, because it kind of requires you to think about stuff you've learned in a different, and apply it in a different way than you've been asked to apply it on questions on your homework and stuff. So it's kind of having you think outside the box, which is what college is all about, right, guys? Thinking outside the box.
One more question. So would you say it has like anything to do with how close in vicinity the electron is like the nucleus, like with the, like the nucleus is pull on an electron?
Yeah, definitely, because the one that's closest has the greatest attraction towards the nucleus, right? And the one that's furthest in energy level 4 would also have the least attraction towards the nucleus. So, I mean, we just talked about 3 different ideas that explain why it would be answer choice G. So it's pretty cool that you pointed that out, actually. Because I wasn't even thinking about it, but there's so many different ways to explain why it would be answer choice G.
I am pretty cool.
No, I said what you said was pretty cool. I'm just kidding. Okay. I wanted to jump all the way down to these. Have y'all started bond enthalpy?
We had a question on it now, so thoughts about it.
All right. I'll give you the area search.
All right, calculate the enthalpy of a reaction when methane reacts with chlorine gas to produce carbon tetrachloride and hydrochloric acid.
I'm not gonna have to.
So,
No, you'll be given that table.
all right, so methane, what's that again? CH4, yeah. What's chlorine gas? CO2, and what does it produce again? Carbon tetrachloride, how do we write that out?
ECl4,
Yep, and what about hydrochloric acid?
HCl.
HCl. What is the primary question we must ask ourselves?
Balance.
Is it balance?
It's balance.
You think it's balance?
Really?
No, yeah.
Don't look balanced to me. How would you balance it out?
Put a 4 in front of HCl.
Okay, that's 4 hydrogens, so now that's 8 chlorines. What do we do from here?
The 4 in front of the CO2.
4 in front of the CO2. Does it look balanced now?
Pretty balanced.
It is indeed balanced. Okay, so from here, what's our next step?
Well, the find like enthalpy of reaction, don't you need to be like the sum of reactants minus sum of products?
I mean, I wouldn't call it reactants minus products.
Or well, like the bonds on the reactant side.
Make plus brain drawing.
Lewis structures, not the
I
reaction.
think some
Yeah.
people might have not learned it yet, so you might want to teach it.
Man like Daniel is correct. So the next step here is to draw Lewis structures. So draw Lewis structures of, so first step is like make the chemical equation and like balance it as we've been doing. Next step is to draw the Lewis structures. So CH4 looks like this. Y'all agree with me, or is it different, or is it that, or does it look different? All right, and then CO2 looks something like this. Y'all agree with that? CCl4 looks something like that. Y'all agree? I'm not drawing the lone pairs for. Should I draw? Yes, we will draw the lone pairs. No.
No, but it's good practice. Right? Always try your own.
What about HCl?
Just H like single bond into Cl.
This is it, right? Why not?
Because there's a long pair on hydrogen.
Why shouldn't you put a lone pair on hydrogen?
That doesn't have that much either.
Yeah, it's because you need only 2 electrons to satisfy it. Let's just testing y'all out. All right, now you do the great equation everybody is talking about. So when you're given bond enthalpies, I don't know how to spell it. Enthalpy. It's the sum. We use this sideways M sigma. It's the sum of the bond broken minus some bonds formed. So bonds broken minus bonds formed, or as you people like to call it, reactants minus products. So next, so what we do is our bonds broken usually refers to our reactants, and our bonds formed usually refers to our products. So let's just write out the numbers now. So what do we put for our bonds broken side? I noticed there's a carbon hydrogen bond, but how many carbon hydrogen bonds do we have on our reactants? 4. So we do 4 times 413. Is that it for our bonds broken?
No.
Or the-
Yeah, so we have the ClCl bond is 243, but how many of those do we have?
Oh, wait, no.
Yeah, I was like, oh yeah, we have 4 ClCl bonds. So basically there's 4 of these types of molecules.
And that's from the balanced chemical equation.
Yeah, plus 4 times 243. That's our bonds broken side. Now we're going to subtract it from our bonds. So for CCl4, it's 339. How many CCl bonds do we have? 4. So it's going to be 4 times 339. And we're going to add this to HCl, which how many HCl bonds do we have? We do indeed have 4. So 4 times 427. So if we do all this, plug it into your calculator, you get an answer of approximately
Give me a second.
Not like that. You're investing in building.
You don't like that, bro.
it's like 5,000 something.
What?
Oh wait, I forgot to do the minus. Never mind. All right,
It's
Not Irish.
negative 440 kilojoules.
Oh, yeah, he's all.
All you have to do is factor out the 4 and then solve it out, but I forgot to do the minus side of it. Negative 440 kilojoules per mole. That's how you calculate delta H from bond enthalpy values. Questions about that?
So why didn't we drop the motion?
We drew up the Lewis structures to see how many of each bond we have. Because like for carbon hydrogen bonds, there's 4 carbon hydrogen bonds in methane. So we have to, that's why we put like the 4 there times the 413. So it's to get like a better visualization of how many bonds there are. Once you get good at Lewis structures though, you don't have to really draw them out. You can just be like, oh, there are 4 in this, you can just multiply it out. But since it's like y'all's maybe first time learning this, I'm gonna draw the Lewis structures. Just to be, number 1, safe, and number 2, it's good practice.
Do you expect us to see this on the exam?
oh,
Oh,
definitely.
100%. 100 million %.
It's also
Sometimes yes, sometimes no. So like most of the time, I think you'll see it where the equation's printed out, but other times you might have to. Thank you.
I have another question. Would you expect us to get one where they give us like the delta H of it? Like they give us the delta.
Oh, yeah,
Would you
yeah.
be expected to like find out like?
definitely.
Yeah, it's just using algebra at that point. So it out.
All right.
No, one shot.
Formal chart? We have not. Have you good, bro?
Nah.
You don't have COVID?
Nope.
Getting scared right now, man. Okay, calculate delta H or not. It should have a delta H, but it's enthalpy of reaction for H2 and Cl2. That should be an arrow also. Combines to produce 2 molecules of HCl. And look at that, we had already balanced that for you. No, right? Just wanna, I wanna see if there's a different one that might be better. Let me know if y'all see one. Ooh. All right, this one's good. This one is exactly like what's his name? Rami. Sorry, I said what's his name? Rami was talking about. Where we, in this case, it's asking us to calculate the CH bond energy. So this is exactly what you were talking about, and you can definitely see this on your exam. We're not going to worry about this one here. That's just a bit of a deeper conceptual question, so don't worry about answering question B. But let's go ahead and go about doing this one. So calculate the CH bond energy given the following data. So we know that the delta H of reaction is equal to the sum of the, let's see, heat of, I'm trying to see. I guess it's just bonds broken minus bonds formed, but it's the energy of the bond broken minus the sum of the bonds formed, which again, like some people want to say, is another way of saying reactants minus products. So let's just assume that you're not going to be given this equation on the exam. So this is something that you should memorize. Okay, so that's first thing that we should mention. And in this case, in the previous example, we were asked to calculate delta H of reaction. But now we're being asked to calculate the CH bond energy. So let's go ahead and write out our Lewis structures. So let's see, carbon monoxide looks like what? Is it CO or C? Is it double bonded?
Every lone pairs on, or either way, there's a lone pairs on carbon, but carbon likes 4 actually.
It likes to have 4 bonds, but carbon monoxide actually is a triple bond.
So the whole year of chemistry dedicated to why carbon has 4 bonds. Because carbon has 4 bonds.
Okay. So, and then we're reacting it with what? 2HH, all right? So hydrogen gas, and this produces, y'all know the name of that?
It's like methane. That's your hint.
It's methanol. So, I mean, it's very toxic for your body, which is why you shouldn't drink methanol. Instead, you drink ethanol. Or I don't know, not y'all, right? Not y'all. But y'all are too young to be drinking ethanol. We all are. So we don't just right? Everyone. Okay.
If you do this much, that's not at all.
Yeah. So you probably would
mean,
be
You're
given.
gonna be asked to draw stuff worse than that.
I know I can.
Oh yeah. I mean, you'll probably be given this maybe. I can't guarantee you that.
Would it be like, because I know we're using iClicker, so wouldn't it be like they just ask what would be the Lewis structure of methanol, and then you have to take this and import the structure?
That's if it's
Probably.
asking about Lewis structures, but this one's asking about CH bond. All right.
Yeah, for that, you can just enter a number, so that is a valid question to ask.
All right, so let's see how many bonds and what bonds are we breaking? So let's go with the first one would be what? What's the first bond we're breaking?
One triple bond between carbon and oxygen.
One triple bond between carbon and oxygen, which has a bond enthalpy of 1072. So 1072, and we're only doing it once. So I'll put number 1 there. And we add to that the other bonds that were broken, and which is what? So we broke a hydrogen single bond, which has a bond enthalpy of 436. And we just broke it 1 time, right? 1 time? 2 times. Say it. I'm looking at the thing for chat.
We don't like it.
You're right. Never mind. Okay, so we're breaking it 2 times. And then from that, we subtract the bond formed, which is everything in the reaction. So what are some of the bonds that are being formed. Yeah, so we're forming how many CH bonds? Okay, so we're gonna be forming 3. But look, this is what we're looking for. So let's just put in a variable x. Because it's asking us to calculate the CH bond energy.
Is there like a way that you would write it if you can, because like with when it came to like standard enthalpy of formation, there was like delta H or like E of reaction.
No, you can write whatever you want. If you want to be particular about it, you can write like,
Is there a variable you should use?
Yeah.
No one's grading for your work, so it doesn't matter.
I mean, if you want to be particular about it, you can put like C bond into H. If you really wanted to. You don't have to.
So we're just gonna say this is X. So we're looking for X, and what else? What other bonds are being formed? Okay, so we're adding a carbon oxygen, which is 463, and we're just one of those, right? So, and we're adding what else?
Now you're adding.
Yeah.
carbon.
Did I? Oh yeah, I did the OH already. So this is for the OH, and then now we're doing the carbon oxygen, which is CO 350. All right. So if you have a calculator like mine, you can plug all this into, and before we get any further, this is all equal to what? Negative 128, right? So the one thing you should be careful about is sometimes they'll give this to you in kilojoules, and then they'll give these to you in joules. Or this will be in joules and this will be in kilojoules. So you have to make sure they're in the same units for this to work out properly. So if you have a calculator like mine, you can just write all this into your thing and then have it solve for X.
I just got one.
Oh, you got one.
I
It's
didn't
gonna
know.
be,
That's
it's
what I'm saying. I didn't know.
gonna be clutch when you get the Jenkins thing. It's gonna take too long. It's gonna take too long. So let's go ahead and I'll show you after. I'll show you after.
That's fine.
Yeah, that's what I did. So 128. Does anyone have an answer? So I don't do all this.
I'm done.
So let's just, I guess I'll simplify. So -1. Okay. So Rami says he got an answer of 417, and that's positive, right?
Yep.
Kilojoules per mole. So Rami did all this by hand, and he got X equals this, which in fact is the right answer. But so I guess the only difference between the problem we did before and this problem is that in this problem we were asked to find one of the bond enthalpies instead of delta H of reaction, like the other problem. So it's not much different, and you could definitely see it either way. I mean, there's really 2 ways to ask this question. It's either by finding delta H of reaction or by finding the bond energy. So is there any questions on any of the previous problems? No questions, we're all good. Ahead. Nice. Do y'all want to do another one of these?
I think we're good. Or I think these.
Guys, speaking for the class.
Yeah.
All right, what about you and you? We're good? We're good? Okay. So this is the exam review for exam 3.
You already wrote it. Or
No.
it's just yours?
No, this is not, this has not been posted yet. It will be eventually. But I didn't know we had a request for formal charge, so I'm gonna see if there's a question with formal charge.
When am I reading the first?
I'm sorry, I'm looking. Okay, there's only one question for formal charge. But we can most definitely make some questions. You want to make some questions, Rich?
All right, let's do it.
I was just asking. If you're.
We haven't done it yet, but we will. And you had a question, Rami? I'm sorry.
Oh, I was gonna ask when you were gonna publish.
Probably the day before the exam.
Oh, for convenience. Yeah, so it'd be like 60 something.
It's actually 100. But they're like multiple places.
Wait,
You're right.
you said formal charge, right?
Formal charge, right?
Right. We're gonna look at into this. The actual thing of
Oh, we
the.
don't know the structure, man.
Calculate the formal.
Okay, let's not.
That's a lot of carbon, right? Those are all carbons, right?
Yeah, those are all problems.
Never mind, you can.
No, let's not confuse them, because not everyone has seen online structure.
What I can do. Yeah, my mind just keeps going organic.
Dude, just
All right, fine.
do acetonitrile.
Acetyl nitrite.
You know what that,
Wait. That just seems to be, wait, no, never mind.
Okay, calculate the formal charge of this highlighted carbon.
wait, do y'all know how to calculate formal charge? Yes or no?
It's like the valence electrons minus.
Number one, right, going to plus electron.
Okay,
I just got three different equations.
It's valence minus unbonded minus half of the bond.
okay, that stuff's way too confusing. That stuff's confusing to me. It's like half the bonded minus the, okay, here's what I do, okay? So what I do to calculate formal charge, I'm gonna abbreviate it as C.
This is Rich's formal charge. Okay, make it official.
It is, so it is the valence electron minus the number of electrons it owns, so the atom owns. What do I mean by that? So right here in this triple bond, right? This carbon, how many electrons does it have in the triple bond? Like how many points are coming from carbon? Yeah, 3. And the way to tell that is how many electrons are in a bond? 2. So each one of the electrons has to come from the carbon. So maybe a different color. So 1.
You're using a highlighter. Oh my God.
No, that was a 0.2 highlighter. 1, 2, 3. 3 electrons here. And there's also another one here, right? From this carbon. So how many electrons is it owning here? For like,
Oh,
for this bond.
Oh,
Yeah, so in total, how many is it owning? So you do, how many valence electrons does carbon have? Yeah, so 4 minus 4 equals,
so in the case of nitrogen, would it be 5 minus 5?
yeah,
Ammonium.
all right, let's do, let's,
That way it's kind of easy.
make it a bit more complicated. That's a C, that's a C.
Oh.
I don't know why this stuff is crazy. I'm just gonna put CH3.
In the quiet study, and I'm just going to drink water. You're almost.
Which one from the guy that opens energy?
Okay, calculate the formal charge of this highlighted nitrogen. How'd you go what?
Nitrogen has a valence, like 5 valence electrons, and it's bonded to 4 things, or it's 4 electrons.
5 valence electron, then it's bonded to 4 things, 5 minus 4, formal charge plus 1.
That's it.
That's formal charge.
Wow, yours is way easier than what I'm on. It was like writing out valence electrons and then subtracting things and I think it burned it.
Yeah.
No, that's too complicated. Work smarter, not harder. Let me see. Let me give you a weird structure and I want to calculate the formal charge of the atoms. So
I like all of them.
of the ones that I highlighted. I need to erase the C6 because I wanted to make it a bigger structure. Okay. So go ahead and calculate the formal chart of the highlighted atoms. This one, this one, this one, this one, this one, and this one. And for and then this one. I'll give you 2 minutes to work on those 6, 7 formal charges. You'll probably need, hopefully you need less than that, but if you need more than that, that's also cool. Let me draw my, to help y'all out, because Lewis structure should have lone pairs. Let me draw some. Like
So
that,
Lewis structure should have lone pairs.
yes,
Now I'm thinking if I put lone pairs, I might have a problem.
I don't think you.
I might. Not there.
What do you like that? What do you, how are you feeling about that bond? The one that might make you look sense.
This. Should that. You don't need my body all the time. Which is fair.
When you're doing okay.
Yeah.
All right. About 30 seconds.
So if you add all these up, what's the charge?
Yeah. Yeah, exactly. Yeah. It is.
You know, it's like the other day, like the rest of the three on tables, like. I know it was like a collaboration, but like this fun works.
I mean, one guy got the credit for it.
The amount of people out of the on. The way it's unrelated.
No, it's pretty fun.
Or the junior.
Is that like playing genius?
All right.
Crazy part that the periodic table hadn't even been completed.
All right. Everyone. Are we ready? All right, let's start from the right and we'll work our way across. So this oxygen, that's an oxygen, the one with the O. What did y'all get?
The one top right. Or bottom right.
This one here. What?
Positive one.
So we got one person that says, 2 people that say positive one. And that's a really big part. Positive one. I can agree with positive one. And if we do the math, it is the number of valence, so formal charge equals number of valence electrons that it normally has. You can find that on the periodic table, minus the number of valence electrons that it has in that specific scenario. So if we draw those in blue, oxygen definitely owns everything in its lone pair. And it owns half of each bond, right? Because each atom in a covalent bond, each atom contributes 1 electron. So oxygen owns each of these electrons in blue. So it would be 6 minus 5, give you a formal charge of +1. Kennedy, what did you get for the next one? It's fine. I asked you what you got for the next one. Oh. Yeah, man. Anyways. All right. So for the next carbon, right below that oxygen, that carbon owns half of that bond, right? So I usually, what I'll do on a test is I'll really draw out these little dots on each bond and say, okay, this carbon has these many, or this many electrons in this specific scenario, right? So then we do formal charge equals number of valence electrons it would have, or carbon normally has, found on the periodic table, minus the number of valence electrons it has in this specific scenario. So it has 4, so it'd be 4 minus 4 equals 0. Let's jump to this nitrogen here. What did y'all get for this one? One person says -1. Okay, so nitrogen has how many valence electrons typically? 5.
Mine.
And it has, in this scenario, it has 1, 2, 3, 4, 5, 6. So -1. So I can agree with -1 as your formal charge. Moving, we already did one kind of like this. We know carbons, every time carbon has 4 bonds, you'll realize it has a formal charge of 0. So what about oxygen in right here? 0. And you'll realize eventually that every time oxygen has 2 covalent bonds, it has a formal charge of 0. So we can do the formal charge calculations. So it has 6 normally, and it has 2, 4, 5, 6. So 6 minus 6 equals 0.
Armand said like every time oxygen has 3 bonds, +1, 2 bonds, 0, and then 1 is negative.
That is exactly right.
What would be the most
That
polar
is-
bond?
What?
What would be the most polar bond?
Most polar bond? Probably
Because I want to know.
looking for an oxygen, probably one of these.
Hydrogen, oxygen.
No, oxygen to hydrogen.
Is the thing that you said about doing being like -1 with 1 bond always like that?
That's what we just, yeah. That's what Rami just said.
Like it almost is a bit, no, that's. Yes.
If oxygen has 1 bond, it always has a -1 formal charge, yeah.
Sure.
What about this one, this funky thing over here on the left? This oxygen. -2, right? Because oxygen owns each of those electrons in red. Oh, wait, negative.
Wait, no,
two.
positive.
Oh, no, sorry, I didn't realize you said negative. I just assumed Rami was right. Okay, so 6 minus the amount it has, 4, gives us +2. Are you gonna see this in nature? Or anywhere? No, you're never gonna see a +2 oxygen.
Is there?
It's just 2 unstable.
Oh.
We're actually
An oxygen with a -2 formal charge possible.
theoretically, yeah. Are you gonna see it? No. You can put it. Oh, wait, what did you say?
Still with a -2 formal charge.
Oh, negative.
That is possible.
Well, oxygen always has a -2 formal charge in covalent compounds. So something like sodium plus sodium oxide, so Na2O. In this case, its formal charge is equal to its oxidation number, so -2.
Yeah, it's the only case where we'll see a -2 oxygen.
This one is like shit.
In an ionic compound, yeah. Yeah,
Are we gonna learn that later?
I mean, you've already heard.
Fair enough.
and looking at this last oxygen right here, it owns it owns both of the electrons for each lone pair for sure. And then it owns one of those electrons involved in the bond. So it would be 6 minus 7 equals -1. So general rule, if you have a carbon with 4 bonds, it has a formal charge of 0. A nitrogen with 2 bonds, always gonna have a formal charge of -1. Oxygen with 1 bond has a formal charge of -1. Oxygen with 2 is happy, it has a 0 formal charge. Oxygen with 3 bonds, +1. And then for this class, you may see something like this, because we're just teaching you formal charge. But going forward, you're never gonna see anything like this.
What do you feel, like,
Gen Chem 1, because we're teaching you formal charge. Like technically, this thing has a formal charge of +2. Are you gonna see that going forward? No, because it doesn't exist. So only for the purposes of learning formal charge, we have you calculate the thermal charge of that oxygen that's never gonna be in existence.
So for when you see
Probably, whenever Rich gets around to it.
Great, send it out.
Yeah, I'll send it out.
Pop off.
All right, without that, y'all can go ahead and. Yeah, leave. We do have a session tomorrow at what time, Rich? 2:30. And I expect to see John whipping up some spaghetti there. So
Whatever. See
have a
ya.
good one, everyone. Oh, Taylor, nice seeing you, Taylor. You're welcome, Taylor. You have a good one. Hope everything's going well. See you tomorrow. Hey, you should go to the in-person session tomorrow. It'll be nice to have someone in our Friday session. We never have anyone in our Friday session. Oh wait, Rami's pulling up. You have 6 tests next week. Okay, you get a pass tomorrow. You can go study for it. Go ahead, Johnny.
Yes, yeah.
Good luck on your
But I
test,
know you
Taylor.
miss me. I know you miss me. Like,
Yeah, look, it's Taylor. You know Taylor?
yeah, I know Taylor. Hi, Taylor.
See you next Thursday in person now. All right, Taylor. Sounds like a deal.
Hi, Taylor. Oh, she left already?
Now she's there, man. She's just leaving you on red, man.
This guy. She's still typing. See,
She's-
she's still typing.